Okay, yeah, thank you, Eric. And yes, welcome everyone to this webinar. My name is Jana Zillmann. I'm a research director at CICERO, Center for International Climate Research, and I'm co-hosting this webinar together with Alessio Curio as part of the Knowledge Action Network on Emergent Risk and Extreme Events, the working group on modeling and insurance. And today, I'm very pleased to have Wim Thiery, Professor Wim Thiery, as our guest to speak on a topic that is very relevant in terms of the future outlook for our children. The kids aren't all right. Wim has done his postdoc at ETH Zurich on historical and future impacts of irrigation on climate extremes. And then in 2017, he was appointed as a research professor at the Free University in Brussels. And there he established the B Climate Group, where the interest of the groups are land-atmosphere interaction, climate extremes, global climate modeling, land management, early warnings of storms, and global scale climate impact modeling. And I guess this is what we also see more about today. And yeah, the Forbes magazine also elected him as a member of the Under 30 Europe class, bringing together the brightest young entrepreneurs, innovators, and game changers in Europe. And that said, I'm very pleased to have you here with us today as a speaker, and I don't want to waste more of our precious time. I give you the floor, Wim, and after your talk, I think you said it's about 40 minutes. We will have time for questions and discussions. There is always the opportunity to write questions in the chat. We can pick them up after the talk, or you can raise your hand after the presentation and ask your question directly. So, okay, so Wim, welcome, and the floor is yours.
Thank you very much, Jana. Thank you for the kind introduction, and also many thanks for the invitation. It's an honor to be here. So yes, the title of today's talk is The Kids Aren't All Right, and maybe a bit peculiar title. Actually, when I gave this presentation recently, some of my colleagues came to me and asked me whether my kids are all right. But I can tell you now that indeed my kids are doing fine. And this presentation is actually not about my children, but about children in general. That said, let me nonetheless start by showing a picture of one of my three sons. So this is Gaspar, and Gaspar was 0 years old in 2020. Now,
good afternoon.
On the left, you can see my father.
Thank you, very pleased to meet you.
Hi. So, and on the left, you see my father, and my father was 60-year-old in 2020.
Oh, I can simply, say hello, but
so, yes,
yeah,
sorry.
just very quickly, I can switch on the video camera for a moment, and I need
Yaro, I think you are.
Irene.
Yaroslav, could you hear me? Yeah, I think he's in the wrong call or something.
Okay, thank you. I'll continue. So I have also two more other sons, but they have ages which are a bit more difficult to calculate with. So let me just continue with this setting. So I want to like to ask you a question at the beginning of this talk, and that is, can you imagine for yourself the age of people that are close to your heart? Maybe your children, maybe your parents, maybe some friends. Keep their age in mind. And then we can ask the next question. And the next question is, will a newborn experience more extreme events to a 6-year-old? So maybe I can invite you all behind your computer to raise your hand if you think that the answer is yes. Unfortunately, I cannot see you, but I'm just going to assume that we have a bunch of experts on the call here and that you will all raise your hands and say, yes, of course. But then comes the next question. And the next question is, how much more? And I think this is something as an impact modeling community that we have to realize that this is something that we haven't really quantified yet. Now, I think this is a very important question. I think there's three reasons why this is an important question. The first reason is that this research question is one of high societal relevance. Now, since late 2018, young people from around the world have been leading climate demonstrations. Here's a picture from a recent demonstration, from a demonstration in Brussels. And you might all have heard of the Fridays for Future movement, which gave rise to a huge surge in societal debate regarding intergenerational justice. Now, these climate strikers and these climate advocates, they usually are a group of young, diverse people. And at the same time, their actions continue to receive fierce criticism. And in many cases, these criticisms are coming from older people. Now, meanwhile, governments' actions are falling short of achieving the emission reductions that are required to stay within the limits of the Paris Agreement. So this tension between insufficient ambition and the wishes of the young people are risking to turn into a generational conflict. And you might have heard of this phrase, "Okay, boomer," which is somehow exemplary of this tension in between generations and the need for intergenerational justice. Now, the second reason why this question matters is the issue of climate litigation. So I'm talking about litigation, not mitigation. So litigation climate litigation is when people sue governments or private companies generally for their lack of ambitious climate policies. And there is a famous case of Eulerian in the Netherlands where the Dutch government was condemned for their insufficient action, and in response to this case, they increased their ambition. We have a similar case ongoing at the moment in Belgium. It's called Klimaatzaak, and we expect to have outcome of that in the next weeks. Also, recently, you may have heard that there's basically every week there is a law case on the news. Last week we had the case of Shell being where the court ruled that Shell has to increase their ambitions and cut their emissions by 45% by 2030. So we have these lawsuits all over the place where in many cases young children are suing governments or companies. And so it is a really important question in that perspective. Is a 15-year-old or is a 5-year-old more entitled to start a lawsuit than a 60-year-old? And it's actually that question that inspired me to conduct this research. But there's also a third reason, and this is a scientific reason, because it's also a scientifically very interesting question. And why is that? That's because it links to this classical difference between the Eulerian and Lagrangian perspective. Yeah. So while this is a very common perspective in atmospheric sciences, it is not at all at the moment on the radar, I would say, in climate impact research. So very quickly, what is the difference between Eulerian and Lagrangian perspectives? Here, I'm exemplifying this with a short schematic. So we have here Mr. Euler, who is standing on a bridge, measuring the temperature of the water of the river flowing below that bridge. And he is measuring the temperatures rising at 2 degrees per hour. Now, at the same time, we have Mr. Lagrange, who is sitting in a boat flowing on the river, measuring the same quantity, water temperatures, but he is finding that temperatures are dropping at 1 degree per hour. Now, both are correct within their point of view, from within their framework, and it's just a different way of looking at things. And as I said, this is quite common distinction in atmospheric research, but not at all at the radar of impact science. Most of the studies that we are conducting are, and if not all, they are, I would say, Eulerian studies, whereby 2 windows of time are compared to each other. In this particular example, a study led by Stefan Lange, which was published last year in Earth's Future, showing for 6 extreme event categories, the change in land area annually exposed to these extreme events. And the x-axis here is showing global warming levels. But in essence, this is a comparison of time windows. So let's zoom a bit more in on this one category here, the heat waves. So again, I'm showing here a picture of how we are typically conducting our research. So this graph is showing the evolution over time of the land area annually exposed to heat waves. X-axis is time, y-axis is this variable, and we can show this evolution under different scenarios, different future temperature trajectories. In this case, under 1.5 degree warming scenario, we see that by the end of this century, about 20% of the land area will be annually exposed to heat waves. Under 2 degrees of warming, this increases to almost 30% of the land area. And under current pledges scenario, the land area annually exposed to heat waves increases to almost 50%. So this is under this particular heat wave definition. But today, we are in 2021, last year in 2020, and in this period, people are living of a certain age. If we look at people who are 60 years old in 2020, this is the average lifetime of these people. They will live on average until 2030. Now, newborns on average, in contrast, they will live on average to beyond 2100. And so they will live to see the day when these scenarios really start to diverge from each other. So in this study, the main idea of this study is to integrate the exposure of an average person within a birth cohort to extreme events across their lifetime. So we calculate life accumulated extreme event exposure. And this is what this looks like for these 60-year-olds and these newborns. A 60-year-old will on average experience about 4 heat waves across their lifetime. And you can see on these bars, which represent the different scenarios, that this exposure is very much the same across these different scenarios. Now, if we look at the newborn in contrast, we see that there the absolute extreme event exposure greatly depends on the scenario. So under 1.5 degree warming, a newborn will experience about 17 heat waves across their lifetime, whereas under current pledges, this is almost 30 heat waves. Now, these absolute numbers, and this is quite important to realize, are of course depending on the definition of the extreme event that you employ. The more stringent your definition, the less extreme events a person will experience. So a way to overcome this limitation is to not look at absolute exposure, but at relative exposure. So what we do is we calculate these exposure multiplication factors, which are showing the factorial increase in exposure compared to a reference person. And here in this case, the reference person is the 60-year-old. So if we calculate these exposure multiplication factors for a 60-year-old, they will be 1 per definition. Okay? The exposure multiplication factors of the newborns are given here, showing that under 1.5 degree of warming, a newborn will experience 4 times more heat waves across their lifetime compared to a 60-year-old. Whereas on the current pledges, this will be 7 times more compared to a 60-year-old in 2020. Now we can do this analysis for all age cohorts born from 1960 to 2020, and then plot the exposure multiplication factor as a function of age. And that's what this graph is giving us. Here on the x-axis, we have age, on the y-axis, the exposure multiplication factor. And what you can do now on this graph is look up the age of your beloved one, and then for each of these 3 scenarios, you can find the heat wave exposure multiplication factor for this person relative to the reference person. Now, how are these results obtained? They were obtained by combining 5 sources of data. The first one is global scale impact projections available from the Intersectoral Impact Model Intercomparison Project, EasyMIP, phase 2B, EasyMIP 2B. We also used global mean temperature trajectories from the IPCC special report on 1.5. These are the 3 trajectories shown here, 1.5, 2 degree and current pledges. And then we combine these data with 3 sources of demographic information. The first one is life expectancy data per country and per birth cohort. Then we have gridded population reconstructions and projections under SSP3 available also through EasyMIP. And then finally, we have the cohort size data per country from the Wittgenstein Center in Vienna. Now, one technical slide here with some nitty-gritty details. The EasyMIP data consists of simulations with 15 impact models spanning 5 different sectors: global water, biomes, agriculture, tropical cyclones, and then heat waves, which links to health. These impact models, they were forced by 4 bias-adjusted CMIP5 GCMs under PI control, historical, RCP 2.6, 6.0, and 8.5. In total, we have a database of more than 270 global scale impact projections and more than 100 pre-industrial control simulations, which are on average more than 500 years long. We use this data set as damage functions, as lookup tables, to get annual extreme event occurrence under different global mean temperature trajectories, the ones that we took from the 1.5 degree report. So we really use a GMT anomaly as a way to translate the data from the RCPs to these 1.5 degree scenarios. Once we did that, on annual basis, we can calculate this life accumulated exposure across age cohorts, given that we know the life expectancy of these cohorts. This analysis is conducted at the country scale for a range of birth cohorts, and then we aggregate this information in space to the regional and the global scale. And while we perform this spatial averaging, we account for within country population density variations. So imagine, for instance, a country like Russia, where people are going to live very concentrated in a small part of the country, so account for that. And we also account for between country cohort size differences, in the sense that in specific countries, a particular age group may be larger than another one. And so by doing all of these steps, we encapsulate spatiotemporal changes in hazards, life expectancy, and population dynamics. But it's important to say we focus on exposure to hazards. We don't account explicitly for vulnerability in this assessment. So one more method slide here. So what I've shown so far was for 3 future trajectories, temperature trajectories. But what if we would like to do this in a more continuous scale, such as done in the burning embers of the IPCC reason for concerns framework? So this is an example of a burning ember from the land report from 2019, and I was very fortunate to be part of the team developing those embers. What is shown here is the risk from wildfire damage under different global mean temperature increases. And this is a very important tool to communicate the risks of climate change to stakeholders and the general public. Yeah? So you have these 4 categories from undetectable to moderate, high in red, and then very high in purple. Now we've also worked on a review paper of these figures and of the way how these are being developed in the IPCC, and this is published in a paper last year in Nature Reviews Earth and Environment. So what if we try to work towards such a burning ember plot, but taking this age factor into account? If we want to do that, we need a range of future temperature trajectories, and I designed 28 synthetic temperature trajectories shown here in gray, taking into account 5 scenarios, one where a constant present day temperature, one with a constant increase, a linear increase to 3.5 degrees by the end of this century, and then these 3 marker scenarios from the 1.5 degree report in between, and the rest of the scenarios are just interpolation between those 5 scenarios. So for each of these 28 scenarios, I can then repeat my analysis and then get a continuous picture. So the figure will look like this. On the y-axis, we have this global mean temperature change relative to the pre-industrial. On the x-axis, we have age, and we can now fill this 2D space with exposure multiplication factors. And this is how the result looks like. Yeah? The colors represent these multiplication factors going from 1 to more than 30 in the highest cases. So what is important is that the reference person for these multiplication factors is now a person living under pre-industrial control climate with a life expectancy of the year 1960. So this is the reference person, a person that is not experiencing climate change. And given this reference person, we find that under 3.5 degrees of global warming, newborns will face 44 times more heat waves accumulated over their lifetime compared to this reference person living on a PI control climate. So this is for heat waves, but thanks to the ISIMIP model database, we can now do this analysis for a whole range of extreme events, and we selected here 6 extreme event categories: wildfires, crop failures, droughts, river floods, heat waves, and tropical cyclones. Yeah? These projections for these impact categories were derived with these impact models that you are all familiar with: WaterGap, LPGML, ORCID, LPG gas, joules, and so on. So these are at the usual suspect global scale.
At the beginning, because there was a little bit confusion about, when the whole
All these simulations are publicly available
okay,
through
so this is,
Grid Federation.
it actually starts with 10:30.
Please, everyone, if you would
Everywhere
like,
we send from 10 until 13,
please,
13:30.
Jaroslav and
this
everybody
is the
else.
website, this is the
Hello?
Eric, I think he cannot
this
hear us
one
for
something.
some reason.
But to keep an eye on.
Okay, good. So these extreme events have been defined in the study of Stefan Lange, and we are using that impact database. So for heat waves, we already have the burning amber plot developed, and we can now do this also for the 5 other categories, and this is how the results look like. So the color ranges for all these categories range from 1 to 4, except for heat waves, where they range from 1 to 30. So the general result here is that live accumulated extreme event exposure consistently increases towards higher warming levels and for younger
No,
ages.
3.5. So we have planned for 2.5, and then I seen, there were contradicting indication on the registration side. And
okay.
now
I'm
it's
trying to continue.
now it's
I'm not
from
quite
10
sure.
until 13:30.
I removed him now from the. Okay.
Yeah, thanks. That's a good idea, I think, to remove this person from the call. Thanks. So the historical changes in climate impacts have had little to no effects on live accumulated extreme event exposure. So if you're above 55, you don't see the effects of climate change. But this rapidly changes for younger cohorts as they start experiencing the impacts in the coming years and decades. Now, if we take one example, a 6-year-old under 3 degrees of global warming, this child will experience twice as many wildfires and tropical cyclones, 3 times as many river floods, 4 times as many crop failures, 5 times as many droughts, and 36 times as many heat waves across his or her lifetime compared to the reference person. So these are very high numbers. Another thing to point out in this figure are the gray lines. So the gray lines are threshold probability isolines. So what we did is for each point in this 2D space, we calculate the probability of living that life under pre-industrial climate conditions. And we use the bootstrapping to generate a large ensemble of pre-industrial control chunks. So if you are above and to the right of this line, you have less than 1 in 10,000 chance of living that life under pre-industrial control climate. So the probability is lower than 0.01%. So we call this living an unprecedented life. If you are above or to the right of that line, you will live an unprecedented life. And what this shows is that people older than 55 will live an unprecedented life only for heat waves and crop failure, where you don't see gray lines, where in fact every age cohort under every warming level will live an unprecedented life. But you see that people between age 0 and 40 will live unprecedented lives. In addition, also for droughts and heat waves at 1.5 degree of warming or more. Now we can, in the next step, aggregate this information across the categories and generate a graph for what we call extreme event exposure in general. Now, we did this by computing the geometric mean across the exposure multiplication factors. Why did we do that? Because the absolute and also the relative changes are quite different between the categories with very strong increases in heat waves. So this approach makes sure that a 5% increase in one category counts as much as a 5% increase in exposure in another category. So again, these results show that if you're aged under 10, you will face an extreme event exposure of, 4 times more extreme events on the 1.5 degree of global warming. And children younger than 8 will experience more than 5 times a 5-fold increase in extreme event exposure under 3 degrees of global warming. So far, all of these results were on the global scale. In the remainder of the presentation, I'm going to zoom in onto different regions and eventually countries. So we show here in this graph the results for different world regions, and these world regions were defined by the World Bank. Here we have the exposure multiplication factor under current pledges, so only one scenario for the different age groups. And the results of this show that there is one region but there is a very marked increase in life accumulated extreme event exposure. This is the Middle East and North Africa, where all age cohorts younger than 25 will face at least a 7-fold increase in extreme event exposure. Now it gets even more interesting when we group countries not by world region, but by income category. And again, income categories are defined by the World Bank, and there are 4 categories: low income, lower middle income, upper middle income, and high income. Very clearly in this graph is visible that young people living in low income countries will face the strongest increases in extreme event exposure. Now, what is important when you look at this analysis is to realize that this is just for the average person living in that cohort, the average person in a low income country living in a particular cohort, but just the average. It doesn't account for how many people are actually in this particular situation. And this is what this slide is what I'm going to explain in this slide. So here we have a pie chart showing the relative sizes of 60-year-olds across these 4 income categories. And you can see that in high income countries, the 60-year-old make up a relatively high fraction with about 22% of all 60-year-olds living in high income countries, and only very few 60-year-olds living in low income countries. If we look at the 40-year-olds, you see that this already starts to change, whereby more people live in low income and lower middle income, almost half of the people now. And if we look at the 20 years on newborns, especially the newborns, you see that more than 2/3 of newborns live either in low or lower middle income countries, whereas only 10% of newborns live in high income countries. So we can now calculate the multiplication, visualize the multiplication factors in such a way in these concentric circles. Here in one example for river floods, the exposure multiplication factor relative to a 60-year-old, again, is 1 per definition. So we have this pie chart, but then it changes for the different age cohorts. If we zoom in onto the newborns, you see that newborns in low income countries will face more than 2-fold increase under 1.5 degree, more than 3-fold increase in life accumulated exposure under 2 degree warming, and a 4-fold increase under current pledges scenario. So again, we can do this for all the extreme event categories. And what you see when you look at this graph, the main take-home message is that people in low-income countries and lower middle-income countries will be disproportionately hit by climate change, and that there's many people, young people, in those conditions because of the large cohort sizes in those groups. Now, one question that you can ask in this context is, okay, there is climate change, but there is also an increase in life expectancy, right? Life expectancy has been increasing over time at the global scale from about 70 in 1960 to more than 83 in 2020. And you can ask the question, what is the contribution from this increased life expectancy versus the increases in hazard occurrence? This question is especially relevant because there are strong differences in increases in life expectancy. In Afghanistan, for instance, life expectancy increased from 58 in 1960 to 77 in 2020. Whereas in Sweden, there was only an increase by 9 years from 81 to 90. So there are strong spatial differences. And now to isolate the effect of increased life expectancy from changing hazards, we calculated the pure effect of increased life expectancy from the PI control simulations. And the resulting graphs look like this. So here we have the absolute extreme event exposure, so not relative, but absolute exposure. In light blue, we have the exposure under the average exposure under PI control climate, so the extreme events occurring in a world without climate change. And then in green, we have the contribution of increased life expectancy, and in purple, the contribution from climate change. Now you see that the climate change signal is clearly dominating the whole picture, the whole increase. In fact, 98% of the total increase in absolute exposure can be attributed to increasing hazards and only 2% to increased life expectancy. There are very little regional differences in that. In low-income countries, lower middle and upper middle income countries, it's also 98%. And in high-income countries, the contribution is even smaller. Only 1% of the increase is attributable to increased life expectancy in this case. Good, I'm coming slowly to the end of my presentation, and let's, for that, zoom in a bit more, even more into the in space. So the actual analysis was conducted at the country scale. So we can also draw up maps that look like this one, where we show the exposure multiplication factor for heat waves under current pledges for a newborn compared to a 60-year-old. You see in this map, dark red colors everywhere, a strong increase in life accumulated exposure in basically every country of the world. We can then show the map, the exact same map, but for the 1.5 degree scenario, where you see that, again, increases in every country, but the increases are less pronounced compared to the current pledges scenario. And this highlights the local value of global mitigation, in that sense that in every country there is an added value in terms of heat wave exposure for limiting global warming to 1.5 degree relative to the current pledges. We can also do this for the aggregated exposure for the current pledges compared to 1.5. And again, you see this clear added value of global scale mitigation for local extreme event exposure in most countries. Now, I want to stress here that the more you go in finer scales, the more uncertain your assessments are. We have to be careful with looking at individual countries when looking at these maps. So I'm arriving at my last slide now. The key points of this work is that we now, for the first time, quantified life accumulated extreme event exposure, highlighting that younger generations will live an unprecedented life and will face strong increases in extreme event exposure, even under low-end warming scenarios. And these results, these sobering results, have strong implications for intergenerational justice and potentially also for climate change litigations. In fact, I was already asked if the results could be used in one of these cases recently. If we look at the 6 extreme event categories, we see that the heat wave increase dominates increased absolute exposure to hazards. And this is why when we aggregate across the categories, we have to account for this by using the geometric mean. We're not talking about impacts, we're talking about exposure. So it could be that an extreme event category generates one particular type of extreme event generates more impact than another one. So that's why we focus here on exposure instead of impacts. Regionally, there are strong regional differences, with regionally up to a 9-fold increase in exposure for newborns under current pledges scenario. And generally, this highlights the clear added value of climate change mitigation. And finally, the strongest effects occur in low-income countries where almost half of today's newborns live. And this is a sobering message, and we have to stress this message in the sense that we want to safeguard the future of young generations by doing everything we can to stick to the limits of the Paris Agreement. And on that note, I end my presentation and would be very happy to take any questions. Thank you very much.
Yes, thank you very much, Wim. And I very much agree with your conclusions. And of course, these results are, I hope they are eye-opening for many that have used lots of arguments. Oh, like what you said, like the impact is more because of the increased life expectancy, or all these, these reasons we hear for not acting or not taking the results or some of our results that we have shown in the climate projections serious enough. And I think your presentation is very strong because you really show the impacts by age, like the 60-year-olds, and we really can see now with these results that those that make the decisions today are basically those that are least affected by climate change. And I guess that's why we don't see much action. But with these cases in the beginning, that you outlined with the liability and now the law cases that kind of get now some momentum. Your results are so important. And I guess I have a question related to that. I don't see any. Oh, yes, I see one question. No, it's from Jaroslav. It's excusing, but I'm asking you my question now to you before we maybe collect more questions in the chat. So please, everyone, be active and ask a question in the chat or raise your hand, and I can take the questions from the chat and yeah. Anyway, but relating to these cases where kids now or young people going to court and claiming their rights for a safe future, what do you think in terms of the reliability of your results? How can you how can you use these results in court? Because I mean, there has been earlier. It was claimed that we need attribution studies to do something like event attribution to support law cases. But then there was always often a problem, like how robust are the results, how can we upscale them, or how are they relevant for a specific case and useful in court cases. But your results, what is can you kind of reflect a little bit how you see that these results could actually be used for these law cases?
Yeah, thanks, Jana. That's a very good point and a very good question. Of course, it's not really my expertise, I guess, as you know, but I can say a few words about this. First of all, I think that impact attribution has a great potential for being used in litigation. There was this case in Germany where the Peruvian farmer sued RWE because he was living in a village below a glacial lake, and there was, with climate change, increased glacier melt, and this increased the risk of a glacial lake outburst flood, a GLOF. And it's only a matter of time before the dam breaches and the town will be washed away, and this farmer's house will be gone. And so this is a clear example where attribution is really important, because the rising temperatures locally had been attributed to greenhouse gas emissions, and then the local glacier melt had been attributed to the increase in temperature. So there is this two-step attribution that took place there, and this was directly used in court. So I think that extreme event attribution and event attribution, but also, especially then, hopefully also soon, also impact attribution will be more and more used in this type of examples. I do think that the results that I have here, although it's not strict attribution, it doesn't follow the strict attribution methodologies, but it's also to some extent inspired by this, and in the sense that we also compare to the exposure in a world without climate change. So while we may not be applying optimal fingerprinting or other attribution techniques, we are linking up with that framework, I should say. So I hope that it will be used. And actually, so there was this case of Portuguese children suing the European Union at the moment, ongoing at the moment. And so I have received a request to include that these results can be used there. But yeah, in the end, we decided together that since the paper is still under review and it's not in the peer-reviewed literature yet, it's probably better to wait for this particular case. But I do hope that it will be used in the future. Now, one last point on this, what I think is relevant, is that there was a very recent, like this week or last week, a paper out, and I don't remember the first author, but I know Sonja Semeveratne was also involved, showing that actually, as climate scientists, we are being too harsh for ourselves, demanding too high level of proof. Yeah, actually, in the court, on the ground, in the field, in the cases, actually, more likely than not, is actually already sufficient as proof, according to the reasoning in that study. Yeah? And this is interesting, because we are only going to be satisfied if it's virtually certain or very likely, extremely likely. We want these very high levels of proof, but in fact, it turns out that in practice, you don't even need that high levels of confidence before being able to use the information. So I think this is also quite interesting. And there was also a plea to put more, give more attention to the more likely than not category in the upcoming IPCC report. So I think this is quite an interesting feature that we have to keep in mind. Yeah, thanks.
Yeah, thank you. That is a very important point at the end, exactly. Especially when we generate the summary for policymakers in the IPCC, we focus on the virtual certain or the most highest confidence statements, and as you say, in reality, also other information is very important for decision making. So yes, I have a question by Carsten Haustein, please.
Yep. Hello, everyone. Wim, that's, as always, awesome. We've seen your presentation at EGU. Loved it there. You explained a bit in the session afterwards. But yeah, couldn't help but watch it again. And it's great stuff. It really is. I have a comment and a question in a second, but you just mentioned the Peruvian farmer. So not only has one of my former colleagues in Oxford, Rupert Stewart Smith, just put out his Nature paper where they literally showed that it is attributable to human cause. I'm sure you know that. And then incidentally, one of the last things before the pandemic, I was on a panel where it was also about this Peruvian farmer case. And there the actual lawyer for the plaintiff was present, and she explained what really helps them to push the case, the climate case. And she clearly said all they accept in the court is what the IPCC says. So it's literally like a waiting game, because you can only update it every 7 years. And then Jana and all else who is involved, they have to formulate it with all these stupid uncertainties and stuff. But that's the ridiculous thing. So you can't even have the paper in the literature. They still wouldn't accept it. It's only that then IPCC has to put it there, and obviously so that it can be taken as evidence, and they would use it. So perhaps that's going to change at some point, and I hope it will, because obviously we can't wait 7 years for so many cases. So that was already leading to the communication problem, I suppose. And I wonder, did you actually use that in a communication framework? Because I would love to see what the old white privileged European male, without being, stereotypically biased against any person. But yeah. So have you tried that? Is that a plan? And also, perhaps as a second question, is there any way, or do you see any way to add this one extra element, which would be the health effect? I know it's crazy uncertain and it's hard to pin that down. I don't even think it's helpful to do it, but would it perhaps be possible to essentially estimate the increased risk to die of heat? Because if you turn 70, 80, that's certainly a risk factor. There was just this paper where they calculated all the risk associated with that. That's the two questions.
Thanks. Yeah, thanks, Carsten. Yeah, and great to see you again. Thanks also for the questions and the comments. So about the cases, yeah, I think I also saw this Hamburg lawyer already, and she's very inspiring. I must say, it's also been guiding more and more my research, that this need to give reliable information to society through these attribution studies and so on. Yeah, what I find interesting is that there is really this surge in litigation. So by the time this RWE case, when I was doing my postdoc 5 years ago, it was really, wow, eye-opening, and the first time this happened, showing this could be used. But now you have every week these cases everywhere. So there is also, and this is I think really interesting. There is really several examples where these cases have been successful, and then now you see in every country of the world, basically now groups do the same as in the Urgenda case, as suing the governments. And then the cases against companies are also rising, especially now with increasing numbers of successful cases. So I do think that there is also use of scientific literature outside of the IPCC in specific cases. I do think that this can happen because I also heard that climate analytics, for instance, they get phone calls from law firms when a new paper comes out asking details and so on. So I do think that this is increasingly also happening, but indeed the gold standard will for sure be the IPCC. And it also highlights that the efforts that the community, the climate science community is investing in writing IPCC reports, that this pays off. And I think this is also really important because sometimes, yeah, there's a lot of stress and I see many people invest a lot of energy and then they ask, yeah, why am I doing this? But it is really paying off. So I think this is clearly shown from this. Now, yeah, and I also saw that Nature Climate Change paper, by the way, which is really interesting. So I think it's really cool that these things are happening and that there is this going back and forth between science and practitioners on this. Communication. Yes, we are preparing a communication strategy. So I have been approached by an NGO called Save the Children, and they are going to write a report for policymakers and for the broad audience about including the results of these findings, but also including testimonies of children in low-income countries and so on. And this actually thanks to Jana. So thanks, Jana, for establishing that contact. So that's really helpful, and we are hoping that the paper will be out in time so that actually the results can be used in that report, because Save the Children wants to use the report for their advocacy towards the COP in Glasgow. So they want to make the COP26 the most climate-friendly COP, and they want to also use the report there to show, okay, children are going to face the most impacts, and then now we have this quantified. So this, we hopefully will be able to use this scientific work in that outreach framework. Yeah, and also I hope that somehow we can make it available on a website that people can make their own burning embers or their own plots for their region and their scenario of choice. So that's also something we will hopefully be able to do. And then finally, health. Yeah, so indeed, I think it would be very nice to do it, but indeed, quantifying health, vulnerability is extremely difficult. There's a number of reasons. I think the first one is that the vulnerability is in itself age dependent. So vulnerability is not constant over lifetime, but it is also, so old people are more vulnerable to health impacts. But that's another problem, is that extreme heat waves may not only cause health impacts, but also may cause preterm delivery, may cause learning problems for children. And so these are then other groups, other age cohort, other age groups that are more vulnerable. So the pregnant women are then more vulnerable to this particular impact, while school children are more vulnerable in terms of learning. So we can do this and for one category, but we can never have all impacts included because vulnerability is so difficult to quantify and the impacts are so manifold. So I think this is something I hope to work on a bit in the future, but I think it's going to be very challenging to go in that direction. Yeah, thanks, Castle.
Yeah. Thanks, Wim. And one aspect which you just said is also how you adopt to warming. I think Paris, for example, they really a strict strategy to warn old people if it's hot again, to drink and to take these precautionary measures. Huge effect, and how to quantify that, it's super hard. Yeah, thanks. And I will take one of these plots in my next presentation, that's for sure. Thanks.
Yeah, thanks. And indeed, I fully agree, vulnerabilities can also change over time. And typically, because I have received reviews saying, but yeah, okay, why worry about heat waves exposure in the future? Because anyway, these populations will be so rich, they can just adapt themselves. But it's actually not sure that adaptation, that vulnerability is, in some aspects it will decrease, but it may also, to some extent, in some places also increase. And also the governance strength is a key in that sense, and the projections of governance strength. So there is a paper from Marina Andrijević in Nature Sustainability from 1 or 2 years ago, showing these projections in governance strength, showing, okay, there is still a long way to go before developing countries reach OECD levels of governance strength and thereby can put in place adaptation policies. So we are a long way from that. So yeah, I think vulnerability will continue to be a key issue in the next decades.
Yeah, I think so too, Wim. And I was attending a panel discussion or a presentation discussion at the last conference of the Copernicus Climate Change Service on climate risk and resilience. And there was the keynote speaker who put forward a theory based on the discounting rate from the great old economists. And basically, if you heard this, I mean, I encourage everyone to look maybe at the Copernicus Climate Change Service website for this webinar on climate risk and resilience and listen to the keynote, which was, I got really upset about his startup experiment of like the discounting rate, basically discounting the life of our children is less worse than what our life. And then he claimed that, okay, the history has shown that vulnerability decreased with development over the past, and this will save us basically, because we can expect that with further development we will further decrease vulnerability, and that will compensate for whatever that. So it was shocking. And if you put this presentation of this person together with yours, I mean, this is basically could encourage a very lively discussion, challenging current or whatever, like this kind of discounting economics theory. Anyway, but I also in the panel discussion after this session, I kind of commented on it. Anyway, but I think we need to rethink our discounting in economics when we want to calculate the future impacts of climate change and motivate mitigation much stronger than we do right now. Anyway, I have a question in the chat. Thanks a lot for your excellent presentation, says Maral Habibi. Could you please explain how to adapt the cities in low-income countries to extreme heat waves? Have you heard any practical methods?
Yeah, thanks a lot for the question. It's, well, this goes quite far away from the topic of this talk, but I do think that cities will become the hotspot of heat stress. There is research showing this, for instance, for Belgium with high-resolution regional climate models, that heat stress increase will be twice as high in the cities compared to the rural areas. And this is, of course, where all the people are living. So heat stress will become a key problem in the future. And from a heat wave point of view, it's quite important how you calculate and how you define this. So in this study, we actually use the heat wave definition developed in the team of Jana Silman, so the publication of Russo et al. 2017. That's the definition that we use in this research. And this is accounting for relative changes in temperature only. But so this is dry heat waves. But you can also consider wet heat waves, where you consider the combination of temperature and moisture together. And these may lead to even stronger heat stress. Now, there are studies showing that this will, I mean, there are these very famous papers from the El Tahiri group showing that there will be places in South Asia and in the Persian Gulf which will become uninhabitable by the end of the century under RCP 8.5. But more recently, there was a study from Climate Analytics showing that even under 1.5 degree warming, these unlivable heat stress will become commonplace in South Asia. So there is this strong increase in heat stress in these regions, South Asia, Middle East, but also I think Sub-Saharan Africa and other tropical regions. Now, how to adapt to cities? Yeah, I mean, we see that air conditioning will be an adaptation strategy, but there is also the question who can afford that and who cannot. So there is some issues there as well. And then I think we can work on increasing the albedo of the cities by working with more reflective surfaces, also working with more green roofs to increase evapotranspiration and so on. But the role of urban vegetation is still to some extent also being debated. But yeah, this would be, I think increasing the albedo is the most easy thing to do and the most straightforward thing to do if we want to adapt our cities to heat stress.
Thank you, Wim. Yes, and also thank you to Nick, who put the paper in the chat that I guess you referred to. Climate scientists set the bar of proof too high. That's great. Thanks for the link. And then we have one more question. That will be the last question because we have to close at 4 by Julia. In this, do you want to say it yourself? It's a long comment. Julia, can you please?
Sure, Jana, thanks. No, I was just thinking about the slide where you show that exposure is mostly, or future exposure to different climate hazards is mostly due to climate change, and to a very small degree, it is due to increasing in life expectancy. Yes, this one. And I was wondering whether you have taken into consideration other demographic development variables, such as, I mean, at least in Europe, we know that the population is aging and their urbanization patterns, and people in cities are more affected by heat stress, for example, and this will increase over time. So when you compare this climate change effect and the population or demographic effect, have you included other demographic variables?
Thank you for this question, which is a very good and very important question as well. So what we account for in this analysis in terms of demographic patterns are evolution of life expectancy over time for each cohort in each country. So we have life expectancy for 5-year-olds in Bangladesh, 6-year-olds in Bangladesh, 7-year-olds in Bangladesh, and so on, and this for every country in the world. Yeah. So this is what we account for. We also account for population density within a country. So for instance, in West Russia, more people are living than in East Russia. So when we aggregate the exposure for Russia, we account for the fact that people are living in cities, in coastal regions and so on. So this is accounted for. And the third aspect which we account for is the fact that how many people belong to that cohort. So in the sense that there are more 5-year-olds in Nigeria than in Austria, right? So if we take the average of life accumulated exposure of 5-year-old in globally, we go into a way with the size of the cohort from Austria and from Nigeria when we take this global average, right? So these are the aspects of population dynamics which we take into account. So this implicitly accounts for the fact that you have higher fertility rates in other countries, lower fertility rates in other countries, higher mortality in specific age groups in some countries and not. So what we did also in terms of life expectancy, I didn't say that, but we remove infant mortality, because in some countries like Democratic Republic of Congo, for instance, there is very high infant mortality. So the life accumulation, the life expectancy at birth will be very low. Also the same with Afghanistan, for instance. But once you make it past that critical age of 5, your life expectancy is actually substantially larger. And so we take life expectancy at the age of 5 and we assign that to the birth year, adding 5 years then. Yeah. So this is one way to remove the effect of infant mortality from this analysis. So we are accounting for certain demographic effects and population dynamics in the analysis. Now, what I find really interesting here is that SSPs in general, but like gridded population, but also fertility projections, mortality projections, and so on, they are completely blind for climate change impacts. So gridded future population data that we are using, they assume no climate change, basically, right? So, and this is quite interesting because, of course, the population density may change, but also fertility may change, and also mortality may change, depending on climate change impacts. But these demographic data, they don't account for impacts, for climate change impacts. And I think this is quite an interesting potential also, and there is actually an ERC consolidator in IASA Vienna from Raya Mutarak, who aims to work on that, to close that loop from between demography and climate change impacts. So there is a lot of work to be done, I think, and there's a lot of potential for improvement of the data that we are using in our analysis. Thanks.
Great. Thank you very much. I think we have to close now. It's 1 minute after 4 o'clock. I would like to thank our speaker again for this fantastic presentation and the answering of the question, and this great audience for asking questions. And we will have a summer break now and come back with new webinars from the WISCON after the summer in around September. So I wish everyone a good afternoon and a nice summer break. Thank you very much, everyone. Bye-bye.